Oh, you like astronomy? Can you create a horoscope for me? Yeah, hit that like button if you've ever heard something like that before. But actually there is something in common between astronomers and astrologers. And I'm not even talking about the part of the words or historical connections. Both make predictions. Though it's kinda hard to compare those. Astrologers base their predictions on some effects that were made up hundreds or thousands of years ago when humans barely knew anything about space.
Since then, we've learned so much about the universe that anyone who knows anything about space would realize that those predictions cannot possibly work.
Also, it's been confirmed by experiments that astrologers' predictions are as good as just random guessing.
But predictions that are made by real scientists, that is a completely different story. Sure, they occasionally also turn out to be wrong, but science in this case rejects or reimagines theories, makes conclusions, and we learn something new in any case.
But at the same time, very frequently those predictions turn out to be true, and most importantly, they are backed up by empirical evidence and not someone's fantasy.
In the 30s of the 20th century, soon after the neutron was discovered, Fritz Zwicky and Walter Baade theoretically predicted neutron stars. Jocelyn Bell's discovery of pulsars in 1967 confirmed the existence of neutron stars.
Another famous example is a mathematical prediction of one more planet in our solar system.
And I'm not talking about Planet 9 that has not been discovered so far. I'm talking about Neptune. An unusual behavior of Uranus on its orbit hinted at the existence of another massive planet in the outer solar system. And it turned out to be true when Neptune was discovered.
And there's a lot more instances where, having limited or indirect data or based on calculations, something had been predicted theoretically and then got confirmed.
Massive bodies curve space-time and act like lenses. Confirmed. Black holes in solutions of Einstein's equations. A lot of empirical evidence for their existence. Higgs boson. Detected. And so on and so forth.
Today I'm going to talk about one such example. Perhaps it's not that global, but it doesn't make it any less interesting. I'm talking about Pluto.
I'd like to talk about things that are discussed less frequently. It's neither the discovery of Pluto nor the latest data from New Horizons, but rather what happened in between. How much scientists were able to learn while being very limited in their means of studying Pluto.
My name is Andrei, and this is Cosmos Elementary. I said that I wasn't going to focus on the discovery of Pluto, but I can't ignore it completely. Especially because its existence was also predicted in a way.
The way both Uranus and Neptune behaved on their orbits indicated that there could be another massive planet.
Here though, the story is a little different. Initially it was predicted that the undiscovered planet had to be several times more massive than Earth. But when Clyde Tombaugh discovered Pluto, it was way too dim, hence small, which means less massive.
Right after it was discovered, it was estimated to be as massive as Earth, but then the mass estimate had been gradually lowered until it reached the current estimate of about 0.002 of Earth's mass.
In this case, the thing that was discovered was not exactly what had been predicted.
Pluto is smaller than Earth's moon, and it doesn't get closer than 4.5 billion kilometers or 2.8 billion miles to the Sun. So for decades, we had no idea what it might look like.
There are two obvious ways to find out what a surface of a body looks like.
You can send there a spacecraft and photograph a body from up close, or use a telescope powerful enough to resolve something more than just a point source.
In the case of Pluto, both things have already been done. New Horizons received amazing images from up close.
And the data from the Hubble Space Telescope helped create these surface maps. Doesn't look very impressive, but actually it is quite impressive knowing how small and how far Pluto is.
But there is another way to at least get the idea of what the surface of a body might look like, even if it's resolved only as a point source.
We can make a light curve. It can help scientists figure out the shape of an object even if it's seen only as a point source. For instance, Haumea, a dwarf planet. Using its light curve, astronomers learned that most likely it is shaped like this. A light curve is a graph with time on one axis and the magnitude, or basically brightness, that we see on Earth on another axis. Points on a graph are separate observations and measurements of brightness. If the brightness of an object didn't seem to change with time, we would see a straight line rather than a curve. But if brightness did change, we would see something like this, a curve. There are various reasons for an object to be variable. For stars, it's their activity, or something like a dust cloud, or a planet can temporarily block some starlight.
If it's an object that reflects light, like a planet, or a moon, or an asteroid, then the change in the light curve can be explained with an object's shape.
In the case of the first interstellar object ever detected, Oumuamua, its unusual shape was also determined using its light curve.
Also, albedo, or how reflective the surface is, can be a reason. Some parts can be light and some can be dark.
Haumea's light curve, its rotation velocity, its physical characteristics like size, mass, hence average density, helped astronomers to figure out its shape. But even though in this case the evidence is quite strong, we still haven't seen it from up close. We still don't know for sure what it actually looks like.
There are instances when the predictions based only on a light curve of what an object might look like were confirmed by images made by a spacecraft.
I'm talking about Saturn's moon Iapetus. Before it was visited by spacecraft, astronomers had been making light curves like these.
While orbiting Saturn, the moon brightness changed. It was explained with large light and dark regions on the surface.
So when its lighter side faces Earth, we see a peak on the graph, which represents maximum brightness. But the dip means that we observe the darker side. And when Voyagers visited Saturn's system, it turned out that that had been true. And Iapetus had a weird surface dichotomy with its light and dark hemispheres. You can see it even better on later images made by Cassini spacecraft. So we hadn't seen the surface of a body directly. Then, having limited data, scientists predicted what it might look like, and later that was confirmed by observations.
But in the case of Pluto, to learn what it might look like, astronomers had to use its moon, or a binary companion, Charon. How do you even learn what one astronomical body looks like using a different body? But I should mention that even before the discovery of Charon, there were some ideas what Pluto might look like.
For instance, these light curves were made. As they show predictable periodic changes, you can use it to figure out the rotational period.
Back then it was already known that Pluto completes one rotation in about 6 Earth days.
Also, from those light curves, one could extract the fact that the surface wasn't uniform. There were at least some parts with different albedo.
So while Pluto was spinning, for an observer on Earth, its brightness periodically changed, though it was hard to say how big or small were spots of different brightness.
But then, in 1978,
James Christie discovered the largest moon of Pluto, Charon. The system is sometimes referred to as a binary system, because both bodies orbit a common barycenter that is outside the surface of Pluto.
So the discovery of Charon gave astronomers a new instrument to study Pluto's surface.
And no, I'm not talking about microlensing. It's all about mutual eclipses.
Or occultations, though most papers I've read use the word eclipse, so I'll run with that.
After Charon was discovered, the orbital period was measured, and it turned out that it is the same as the rotational period of Pluto. Both bodies were tidally locked, which means they both always face each other with the same hemisphere. To be able to observe transits or eclipses, we need to see the system edge on, and that's not always the case. Actually, a configuration like this is quite rare. It lasts only for 6 years, and what is worse, it happens only twice in Pluto's orbit. That is once every 124 years.
And can you imagine? We didn't even have to wait for tens or even 100 years. The season started soon after the discovery.
In the 80s, astronomers made lots of observations of Charon or its shadow covering Pluto, and also Pluto covering Charon.
So that gives us unique light curves. So let's say this is Pluto and this is Charon. At that time, they basically were a point source. So when Pluto was not covered with Charon, this point source had a certain brightness for an observer here on Earth. When they are separated, like this, we receive combined reflected light from both bodies. But when Charon, or its shadow, covers part of Pluto's surface, we basically see less of the area. We receive less light, and that shows up in a light curve.
If the bodies weren't tidally locked, that wouldn't be that useful. But as long as they are tidally locked, during the transit, we always see the same side of both Pluto and Charon. But also, an observer on Earth doesn't always see Charon covering the same region of Pluto. Actually, during the mutual eclipse season, Charon and its shadow transits different parts of Pluto.
To figure out how it can help build a surface map, let me bring the most basic example.
Let's just imagine that the Pluto's hemisphere that we can see during the eclipse season actually had two equal halves of different brightness, the dark and the light one. If Charon transited right over the dark half, we would see something like this on the light curve. The half is dark, but it still reflects some light. But if Charon covered the lighter half, we would see a more drastic dip on the light curve, because the half that reflects more light is blocked.
Obviously, it's not a realistic scenario, and yet, if we knew nothing about the surface, but knew the time of the eclipse and positions of bodies relative to each other,
from light curves like these, we would be able to suppose that Pluto had two contrasting halves.
That's the basic principle. Of course, in practice, everything is more complicated than that.
In reality, Pluto obviously doesn't cover the whole half, and during multiple transits, it and its shadow covers different regions. Each eclipse turns out to have its unique light curve. So those light curves were put together, got analyzed, models were created, and it allowed scientists to reconstruct Pluto's albedo map of a certain resolution. And this is one of those maps. Just imagine how clever it was to create such maps way before the Hubble Space Telescope. This alone showed that Pluto had to have a very interesting contrasting surface. It seemed to have a dark stripe, longitudinal variations, and bright spots.
The fact that there is some bright surface on Pluto suggested that there could be some activity that renewed surface, making older and darker surface brighter, and that could point at the existence of an atmosphere. We'll get back to that. And now the important question for the theme of the video. How good was that prediction of what a surface might look like? Well, pretty good.
These are surface maps created from images taken by New Horizons 2 weeks prior to Flyby. The angle is a little different, but thanks to the grid we can see how these maps also have dark equatorial stripes. And this is a screenshot from Richard Binzel's lecture, who studied Pluto for decades and also worked on these maps. On the left is the map made with eclipses, and on the right is the same hemisphere but made with images from New Horizons. Obviously it's not the same, but it's quite close. Amazing.
But that's not all. Way before New Horizons flyby, scientists predicted that Pluto might have had an atmosphere of some sort. And again, to predict that, they used another body, and this time, a star.
In the 70s, astronomers studied Pluto's spectra and saw there hints at the existence of methane, perhaps in the form of ice on the surface.
A little later, it was suggested that at least part of that methane could be in the form of gas, so there could be an atmosphere, though a lot wasn't clear. But the best evidence came from stellar occultations. Before I talked about Charon covering Pluto. This time it was Pluto covering a star.
Pluto, as anybody in the solar system, is way closer to us than even the closest star. Unlike most stars, it doesn't remain fixed in the night sky on relatively short timescales. Actually, even stars move in the sky, but very, very slowly. So it's quite easy to notice the change of the position of the closest planets, but bodies like Pluto that are farther away move more slowly. So by monitoring how the object is moving in its orbit, it is possible to calculate with some precision where in the sky it will be in future. In the case of Pluto, we actually haven't even seen its full orbit since discovery, but it's still possible.
It was calculated that on June 9, 1988, Pluto would cover a star. That would have allowed astronomers to make a light curve of how a star's brightness changed during the event, and that could have given information about Pluto itself. But it's not that simple to observe such an event, even if it's precisely predicted.
Probably some of you had the experience of hearing news about a coming solar eclipse, being all excited and looking forward to seeing it, maybe even a total solar eclipse. Then you looked at the map and realized that it wouldn't be visible from where you lived. The total solar eclipse can be observed from a relatively narrow region in the shadow of the moon. It's a similar thing here, but way worse. Instead of the sun and the moon, it's tiny Pluto and a faraway star. The shadow where such an event would be visible is incredibly small. The best way to observe an occultation like this is not from a stationary observatory, but rather an observatory like Sophia, which is on the board of a plane. This is footage from a different occultation event observations by Sophia made in 2015. In 1988 there was no Sophia, but there was a different airborne observatory, and it successfully observed the occultation event. So, what did scientists see? They got this light curve, and that was very strong evidence for Pluto having an atmosphere. But how does this tell about an atmosphere?
The thing is that the star is very far away. It's a point source, and we cannot see the disk slowly disappearing behind Pluto, as it is the case for solar eclipses.
So if Pluto didn't have an atmosphere, it would look more like this, a curve with a very steep decline. But instead, the brightness decrease is very gradual. And that means that before the star was covered with Pluto, first its light had to travel through a gradually more dense atmosphere, which is why the brightness didn't drop instantly. That's exactly what we see in this light curve. Also, it's symmetrical. The star slowly hides and then reappears. Also, there are some symmetrical peaks that might point at different atmospheric layers and temperature variations. And now try to imagine, what did people who in the 80s worked so hard and spent years studying tiny distant Pluto, and the best they got was this? What did they feel when New Horizons flew by Pluto and sent this image? The atmosphere of Pluto backlit with the sun, what it was like to come all the way from graphs on paper to being able to actually see in such detail and color the proof that you were actually right all along. That's what's different about the predictions of actual scientists.
Thanks for watching. If you enjoyed the video, you can help me out a little bit. You might have noticed that my videos get barely any views, and I try really hard to make those. So I would be really happy if you shared this video with your friends on your social networks or whatever. Thanks again, and links to all of the sources, as usual, are down below in the description. Bye!